Wilkerson, professor of physics at Luther College. We're going to work one or two RLC circuit problems here. This is primarily for the students in Classical Physics 2, Physics 182, but anybody else who wants to follow along, you're more than welcome to. For those of you in the Classical Physics 2 course, spring 2022, when we're filming this, this problem you see sketched out here. The circuit that you see sketched out there is for the problem that is the first one on slide 12 of the PowerPoint presentation we've gone through the last couple of days. So this is what we got for this problem. I better go look at it actually and see if I make sure I remember what it says. I think it says we want the average power dissipated. Yeah, so we're looking at this circuit. So we draw this circuit out and say we want to know what the average power dissipated is. We've got an AC driver with a peak voltage of 12 volts and a frequency. We're operating at a frequency of 2.5 times 10 to the 3 hertz. We have a 220 ohm resistor in series with an 8 microfarad capacitor and a 0.15 millihenry inductor. So pretty standard LRC, RLC circuit that we have right here. And what we know, we've written this different ways. We say the average power is IRMS, ERMS, cosine phi, cosine of the phase angle of the circuit. And so we can look at that and we can say, well, cosine of phi, we know is R over Z, the resistance over the impedance. So we can stick that in. But we also know that the current is IRMS is equal to ERMS over Z. So we can write it that way too if we want to, and write this thing as ERMS squared R over Z squared, the impedance squared. So if we can find the impedance, that seems pretty straightforward for us to do. Then we got this thing figured out. So we've sort of reduced this problem. We know what R is. We can stick R straight in from here. We know what ERMS is. We know what E peak is 12 volts, so we know what we can do there. It's going to be ERMS squared. ERMS is going to be 12 volts divided by root 2. RMS squared is going to be 12 volts squared divided by 2. When you square root 2, you get that 2 out of there. So this is this problem has been reduced then to really finding what the impedance is. And we know that the impedance is going to be Z is the square root of R squared plus XL minus XC squared, square rooted, right? So we got that going for us, and we can solve there. So we need to find out what X sub L is. We know that's 220 ohms right here. And so let's figure out what X sub L is going to be omega L is 2 pi F times L is, in this case, 2 pi times F is 2.5 times 10 to the 3 hertz times 0.15 millihenries, 1.5 times 10 to the minus 4 henries. Okay? Good? Good? We stick that in. I got 2.355 ohms. So it seems like a small number. We want to be careful. Numbers aren't absolutely small or absolutely big. We talk about that a fair amount, is to say you can't look at a number and say, well, that's small. It's all relative to something else. But relative to this 220 ohms, that's not much impedance there. And relative to the fact that you could have your reactance, your inductive reactance could be any value, right? If inductors don't like change, so if you had a very high frequency, this reactance is going to be enormous relative to this 220. So we can, although we don't like to use the language small and large because it doesn't have any real global meaning, we can get away with it maybe in this case to say, because relative, it's 1% of the resistance in the circuit, and it's a very small fraction of what it could be at a higher frequency. But it's also very large relative to what it could be at a lower frequency, so you want to be a little bit careful there. X sub c, we know is 1 over omega c, so we just got to stick those values in like we did here, which is 1 over 2 pi times 2.5 times 10 to the 3 hertz times the capacitance, which is 8 times 10 to the minus 6 farads. When I stuck those numbers in, what did I get? I got 7.962 ohms. So again, pretty small relative to what this resistance is. So the resistance is dominant in this circuit. What that means is, relatively speaking, we're not really far from the resonant peak in this circuit. So let's, we'll come back to that. Let's stick this in. We stick X sub L in up here and stick X sub C in and take the difference of them, square that difference, add it to the square of the resistance, square root the whole thing, and I got an impedance when I did that. If I can read my handwriting, and you know I can, it's 220.7 ohms is what I got. So we just added less than an ohm to the resistance of the circuit right there, and that ended up being, then if I stick that in here and I stick R in there, I got an average power dissipation of 0.33 watts. So work through that, see if you get the same thing that I got if I'm reading the numbers on my page correctly. But now let's think about this. This wasn't part of the problem that was asked there, but it's always good to think about these things, is to say, always drink your coffee. Gotta have your coffee. To say, look, this is mostly a resistive circuit. The impedance that has a very small little bit that's added by mostly the capacitor. So the fact that the capacitive reactance is larger than the inductive reactance suggests to us that we are at a frequency that is below the resonant frequency, but we're not an order of magnitude below the resonant frequency or 2 orders of magnitude below the resonant frequency. So we're somewhere in the neighborhood, within a power of 10 of the resonant frequency and below the resonant frequency, to say what impedance we're getting added from the inductive and capacitive elements is coming more from the capacitor than from the inductor. So let's check that out. Let's see if this 2 pi f is in fact below the peak, the resonant frequency, but not way below the resonant frequency. If you look at the problem that's on the PowerPoint, it doesn't ask you to do this, but of course you're going to do this, right? You're going to think, well, I want to make sure I understand everything I can about this circuit, and so I'm going to go in and figure this out. What we're talking about here is the current as a function of frequency. We expect as a function of, let's make it omega, as a function of angular frequency to look something like this, where that's the resonant frequency. And the resonant frequency is, let's write that down here. Omega naught is the square root of 1 over LC. In this case, we can write this as 1.5 times 10 to the minus 4 henries times the capacitance, which is, I just erased it. I have to look at my sheet because I just erased all of this was on the board. Good planning is what we call that. Times 10 to the minus 6 farads, all to the minus 1/2 power. And I get 2.9 times 10 to the 4 radians per second. Our driver was, I got to look at my sheet again because I erased it. Our driver was 2500 hertz. So omega of the driver, that's omega naught. Omega of the driver is 2 pi times 2.5 times 10 to the 3 hertz, which when I stuck that in, I got something on the order of 1.6 times 10 to the 4 radians per second. So indeed, just what we predicted, omega naught here is 2.9 times 10 to the 4th radians per second. The omega of the driver frequency, angular frequency is 1.6 times 10 to the 4th, so it's less than. We knew it was going to be less than because the capacitive reactance was bigger than the inductive reactance, but we knew it wasn't going to be a lot less than, because the resistance of the circuit was very large relative to this reactance, the capacitive reactance, and it was in fact it's within a factor of 2 of that. So it's down in here someplace is what you're looking at. So that's what we got for that problem, and I think that's enough for this video. Maybe I'll shoot one for another problem, but maybe I won't. I think we've done enough here, thinking about how we, this problem was, we just needed to find the impedance, and once we found the impedance, we could figure out what we needed to do. Then we did a little double check to figure out what the natural frequency of the circuit was and how close we were to the natural frequency, and double check to make sure we were below that natural frequency as we expected from the reactances we got. So hopefully that's helpful for everyone. I hope you enjoyed watching it. We'll have more videos for you in the future. Thanks, everybody.